Okay, so welcome everybody to our third, I guess, CRM McGill Applied Mathematics seminar for fall 2021. It's my great pleasure to introduce to you Jason Bramburger. Jason received his PhD in 2017 from the University of Ottawa with the supervision of Benoit Dion and Victor Leblanc on rotating wave solutions and lattice dynamical systems. Since then, he has been a postdoctoral fellow at Brown University, a PIMS postdoctoral fellow at University of Victoria, and then a acting instructor at Washington University. University of Washington. And as of this year, he is a assistant professor at George Mason University. So as this is a hybrid seminar, if those of you that are participating on Zoom have any questions, you can post them in the chat, and this will be monitored and your questions will be relayed to Jason at the appropriate time. So everybody else, this is a regular seminar for us. So let's enjoy Jason's talk about deep learning of conjugate mappings.
All right, so thank you all for being here, and thank you very much for having me. Thank you to the organizers for putting this on, and thank you for Kevin for being a sort of local host for me. So what I want to talk about today is a sort of melding of machine learning and dynamical systems theory. So as Kevin had mentioned, my background in mathematics is really sort of old school pencil and paper dynamical systems. And so what I've been interested in lately is using deep learning to sort of overcome some of the mathematical gaps, or maybe the analytical gaps that we have in mathematics. So for example, we say there exists a function, but sometimes we want to know exactly what that function might look like, or at least up to some approximation. And so the hope here is that we can leverage some of these modern computational techniques, such as deep learning, in order to give us some quantitative results about explicit dynamical systems. So all of what I'm going to talk about today is coming from a recent paper that I published with Steve Brunton and Nathan Kutz from the University of Washington. That's going to be the primary source for most of the results that I'll show you. Okay, so where I want to start here is my absolute favorite topic in all of mathematics, and that is chaos. So chaos might be one of the most aptly named phenomena in all of mathematics, because when you first see it, maybe as an undergraduate, maybe as a graduate, the one thing that comes to mind whenever you see it is the word chaos. It is perplexing, it is complicated, it looks like it's seemingly random to some extent. And of course, this is what we thought mathematicians in the early days when we saw this, but decades of mathematical research has shown us that this is not the case. In fact, when you have a chaotic attractor embedded in the phase space of, say, some ordinary differential equation, such as the Lorentz equations that you're seeing here, we know that we can decompose that chaotic attractor into infinitely many unstable periodic orbits. And you can use these periodic orbits to really understand the geometry and the topology of a chaotic attractor. We have theorems that tell us, for example, that long-term time averages over chaotic attractors can be written as weighted sums over the unstable periodic orbits. Now, the unfortunate part of all of this is that these periodic orbits are, of course, unstable. But what that means is that you can think of moving across a chaotic attractor as starting close to one of these periodic orbits, following it for some finite amount of time, but because it's unstable, you're going to get thrust away and jump to a neighborhood of another one of these, stay close to it for a while and get thrust away, and continually bounce back and forth between neighborhoods of these unstable periodic orbits. And so what we know is that if you really want to understand the structure of chaos in a system, what you need to do is you need to understand the structure of these embedded periodic orbits. That's what a lot of the game comes down to in this case. And the way that we can do this is we can go all the way back to the late 1800s with the work of Poincare. So at the time, Poincare was really interested in finding solutions to the many body problems. And in that case, you have very high dimensional phase spaces. And what he noticed is that not all of the trajectories are periodic, but they are at least recurrent. They start to come back to the same place in phase space. And this led Poincare to introduce one of the many things that he is now famous for, but that is the notion of a Poincare section. And what he decided to do was to introduce a lower dimensional transverse to the flow subspace into the phase space of the dynamical system and simply track the intersection of these trajectories with this subspace. And then what you can do is you can theorize a mapping which iterates you through these successive intersections with this, this transverse subspace. This theoretical mapping, now of course referred to as the Poincare mapping. And this offers a massive advantage to understanding recurrent behavior in dynamical systems. The first of which is a relatively obvious one, but you get a dimensionality reduction. Now, it's only one dimension less, but it's still a dimensionality reduction. And that comes from the fact that you are moving from a continuous time system into a discrete time system. Now, the real advantage here, if anybody has taken a class in chaotic dynamical systems, you know this, that it's really through these discrete dynamical systems that all of our understanding of modern chaos theory comes from. And in particular, these Poincare maps are used to understand the topology of the attractor, because you can find those embedded unstable periodic orbits from the previous slide by just looking for recurrent points in the mapping, right? You look for fixed points, those are periodic orbits. You look for recurrent period 2 points, those are periodic orbits. Okay, so I gave you advantages, but of course, you know, I tuck this way down below at the end of the paper or something like that, and I say, okay, by the way, there's a slight disadvantage that comes with this. And the disadvantage is a huge one in that it is almost impossible to find an explicit Poincare mapping if I give you a system. So for example, if I ask you, what is the Poincare mapping associated to the Lorentz system? It is nearly impossible to write that thing down. At least I would say it is functionally impossible. So this is really what has preoccupied a lot of my career for the past few years. And really what I've been trying to do is to overcome this question using model discovery techniques. So there is a ton of really interesting methods that are being developed in this sort of falling under the broad umbrella of machine learning that will allow us to discover explicit systems from data. And so what I was thinking about this is maybe I can use this to solve these sort of old questions from dynamical systems and find these explicit Poincare mappings. Now, let me introduce you to the first method that I started using here, which is called the sparse identification of nonlinear dynamics. This is also known as the Cindy method. So this is coming from a paper published in Proceedings of the National Academy of Sciences in 2016 by two of my collaborators, Steve Brunton and Nathan Koontz, as well as Proctor. And so the idea here is a very, very simple one. The idea is that you gather the data that describes your mapping. And so you say, okay, the first, where I started in this Poincare section at X1, I know that that flows around to X2 just by simulating the system. And then I know that if I simulate forward X2, that's going to go into X3 and so on and so forth. So I have a discrete collection of points that are governed by my Poincare mapping. And so what you can do is you can stack this data into two huge data matrices. I'll call them capital X1 and capital X2. And like I said, the fundamentals of this method are extremely simple. And they're probably what most of us would have thought of initially. And that is to just assume that your unknown function has some sort of basis expansion. So the example I'm going to give you is a Taylor expansion. But if you prefer to use Legendre polynomials, you can use that instead, or Fourier modes as well. Anything will work. And you can mix and match on top of that. And so essentially what you get here is you're making the assumption that you're governed by this basis. And so once you put in the data that you know, the X1 and the X2, this leaves you with just a linear algebra problem that you need to solve. In particular, this capital Chi matrix right here is just representing the unknowns. That is the coefficients that you're going to tune in this linear span in order to best fit your data. All right, so the principle, again, is very, very simple. And of course, if you do this right, you should have much more data than you have elements for your basis expansion. So that means more rows than columns. You have an overdetermined linear system, and there are multiple solutions. And so this is really the novel piece of the Cindy method, and it tells you how to select the right solution from this linear system. And it works on this sort of Occam's razor type argument. It says the systems that we work with should be simple enough for us to analyze. And in order for it to be simple, we would like to use the right hand, or we would like to have the right-hand side be as simple as possible. That means it contains the least amount of basis functions. And so what we strive to do with the Cindy method is promote sparsity. And this is done in an extremely simple way. This can be implemented very, very quickly using just any sort of mathematical software, such as MATLAB. And basically what you do is you find the least square solution, and you comb through that solution. You have some threshold parameter. Any parts of that solution that are below the threshold parameter, you throw out those basis elements that are corresponding to it, and then you restart the process with this smaller reduced library. And you bootstrap this back and forth until you eventually converge to your sparse model. Okay, so this is a great idea, and maybe you've seen some of the papers that are associated with this. It's very good at discovering systems as long as you know what should be in your basis. And that is a question I have never been able to answer. If you give me an explicit system and you ask me what I should use for my basis, I'm probably going to pick Taylor expansion because that's really all I can come up with. But very few pieces of data are actually governed by polynomials, and therefore you might not get a very good mapping here. So what I was trying to think about when I was initiating this project was how we can overcome these ill-fit models, particularly when you have chaotic data, this very, very sporadic jumping from one point to the next. And this got me thinking about a really old idea from topology that's referred to as, or this concept referred to as a topological conjugacy. And the basic idea here is that if I have my data which maps some space X back into X by, say, some unknown mapping F, well, the Cindy method is doing a direct discovery process. It's finding F explicitly. But what a topological conjugacy does is it says, find a change of variable, call that H, that transforms your space from X into some other space, say Y, so that you can iterate through Y using a different mapping G. And as long as H is invertible, you have a direct correspondence between the iterates in F and the iterates in G, just using this relation down here. Now, you're probably thinking to yourself, what is the point, Jason? You just told me that finding one mapping is hard. Now you're telling me to find two of them. And in particular, you're asking me to find one that is invertible. But this can be tremendously rewarding if it's done correctly. Because the advantage this offers us, if we can find that change of variable H, it can relate a seemingly very complex system to one that is relatively simple. So let me give you an explicit example of this. This is typically the example you would find in the textbook right underneath the definition of a topological conjugacy. And in this case, your unknown mapping F is going to be given by this piecewise continuous function. So it's a nice tent function that's just like this. Now, that function is extremely easy for me to write down on paper. That function is extremely hard for me to discover with some sort of model discovery process. Why? Because almost no one is going to put a piecewise continuous function on the right-hand side to expand a basis in. So if you think about this from the context of just being given data without knowing what you're looking for, this is an extremely hard problem to discover a Poincare mapping that fits that tent map. But what we know is that if we can find this nonlinear change of variable H, then the Poincare mapping is equivalent to a very, very simple quadratic polynomial. And again, I remind you that polynomials are a good thing partially coming from the fact that I include them in the right-hand side most of the time when I do my model discovery. And so this tells me that F might be hard to find, but if I can do the hard work of finding a change of variable to put this thing in the right coordinates, then finding my mapping G in these new coordinates is an extremely simple process, or at least should be a relatively simple process, because at least I can get the basis elements right. And this is exactly where the neural network comes into play. So what I want to do is I want to implement a neural network to mimic this idea of topological conjugacy. And so the idea here is that the network, when you feed in your current state for your Poincare mapping, once it goes all the way from end to end in the network, the output is the next state. So that means that your network from just the input to the output is the Poincare mapping F. But the inner mechanics of the network are given such that, if you'll allow me to go back for a moment, they're given to mimic this exact diagram right here. So instead of traversing from X over to X, you are going to traverse from X to Y first, then from Y to Y, and then from Y to X. If you are a little bit more familiar with machine learning, this is an autoencoder architecture where you are learning both the change of variable H and the undoing of that change of variable H inverse all during the training step simultaneously. And the effect here is that when you put the input in, it moves through the encoder function, your conjugacy, and it spits out your Y variable, your changed variables. And inside of the neural network, you have a Cindy type discovery process that iterates you through the changed variables. So yn into yn plus 1. And then when you have yn plus 1, you undo that topological conjugacy, eventually spitting out your next iterate of your Poincare mapping. So there's a number of advantages to doing this. I mentioned earlier that this is essentially an autoencoder type process. Now, if anybody actually is familiar with autoencoders, they'll know that autoencoders are typically used as dimensionality reduction mechanisms. In fact, the primary focus for them is for doing this for, say, images. And you can do the same thing here. You can have your dimension of your observable variables X be a much higher dimension than your latent variables Y. And the way you can think about this mathematically is imagine you have a very high dimensional flow, say a 100-dimensional dynamical system. Well, your Poincare mapping and your chaotic attractor might only actually be, say, 1 or 2-dimensional. So you can have a very simple attractor, a very small attractor embedded in a very high-dimensional space. And so what the conjugacy is doing is not only changing variables, but also projecting down onto the latent manifold that is describing this lower dimensional dynamics on the chaotic attractor. Now, another extremely important aspect of this is that you get an improved accuracy for forecasting. So if you want to be able to know where your chaotic system is going in the future, well, this network architecture is much better than just using the Cindy method. And again, this is a fairly intuitive reason, but you're just fitting better mappings. If you're forcing your tent mapping to be fit to polynomials, it's just going to be terrible. You're just not going to do a good job of it. But if you can find that change of variable through the network and then fit a polynomial mapping, you're just fitting everything better. You found the conjugacy and you found the latent mapping. Now, this third point here is really what I care about as a mathematician. And this is the aspect of it that is, in my opinion, the most important. Because this gives you a simple way of understanding the topology of a chaotic attractor. This classifies chaotic systems up to topological conjugacy. This is an equivalence relation. And in particular, what the fourth bullet point is emphasizing here as well is that your dynamical properties of your system are preserved between these conjugacies. So for example, your topological entropy for your system F and for your system G are exactly the same. Time averages are preserved. Your periodic orbits lay in one-to-one correspondence. If you want to find a fixed point of F, find the fixed point of G, and then map yourself back to X space. If you want to find the period 2 points, find the period 2 points of G and map yourself back to X space. And so this allows you to take relatively complex systems, as you're going to see in some of the examples here, and sort of boil them down to their simplest possible systems. So the one thing that is worth asking, that I imagine a lot of us are wondering, is, if I just give you a bunch of data, how do you know if you have low dimensional dynamics in there, right? What is the dimension of the latent variables, y, that you should be aiming for? Because of course, this is a hyperparameter for your system. This is something that needs to be pre-programmed in before the training process. And you can do this again using some theoretical mathematical concepts going all the way back, to the time of potentially Lyapunov, or maybe the 60s with James York. And this comes from the idea of using Lyapunov exponents. So Lyapunov exponents are one of the typical ways that we classify chaotic dynamics. And based on, there's a rigorous definition, but essentially what it says is that it's describing the escape of elements that start close together. So you can think of these as sort of linear systems. And what you're doing is saying, if you initially perturb off at some point, then you ask yourself how you're separating from that point as time goes on, using these linear, just these linear exponential terms. And the presence of chaos is typically marked by your first Lyapunov exponent being positive. So that tells you that every initial condition on the chaotic attractor is moving away from initial conditions that start close to it. And so what you can do with this is you can create what's referred to sometimes as the Lyapunov dimension, or the Kaplan-York dimension, named after Kaplan and York. And essentially what this is they have a conjecture that says that the topological dimension of the attractor in phase space is equal to this d sub ky, this Kaplan-York dimension.
Sorry, Jason, we have a question in the chat.
Sure.
So someone is saying, for the autoencoders,
Yep.
is the second network mathematically inverse of the first one, or an approximation obtained by your training?
Yeah, it's an approximation obtained by a training. You can't just create an exact inverse. So you have to build this into the training steps. Yeah. No, thank you for the question. Okay, so the Kaplan-York dimension is fairly complicated. It's kind of ugly looking, but if you have the Lyapunov exponents, you've got it. You can. This is a one line in MATLAB, for example. And that tells you that your latent dimensional mapping should be approximately one less than that. Now, why do I say one less? Because you're moving to the discrete iterates. You're moving to a Poincare section. And the other point of this is I say approximately because you can tell from my formula for the Kaplan-York dimension that this is a Hausdorff dimension. This thing is not necessarily going to be an integer. Actually, no one would expect it to ever be an integer. So you have this, this approximation component here. Okay. So let me give you an example. Of course, we want to see how this works on some of the most important chaotic systems that we study. And the first of which is my personal favorite chaotic system. I know everybody loves Lorenz, but I feel like Rosler just doesn't get the attention it deserves. And so therefore, I want to start with Rosler. I'll do Lorenz next, but we'll do Rosler first. And so the Rosler system is a three-dimensional quadratic polynomial system. Very, very simple. I imagine many people have encountered it in some form. But what I love about the Rosler system is that when you create a Poincare section at x equal to 0, so that hyperplane when x equal to 0, it has a property that every time x crosses 0, then z crosses 0 as well. So essentially, I've got a one-dimensional Poincare section without doing any dimensionality reduction. So I just want to see how this can perform on this. And in particular, if you plot the current iterate in Y, so I realize I'm sort of moving back and forth between definitions of variables here. In this case, Y is corresponding to the Y variable of the Rosler system. I apologize for that. But if you plot the current iterate against the next iterate, you get this beautiful looking curve. And it doesn't take an expert in mathematics to look at that curve and think that sure looks like a quadratic function to me. But unfortunately, you know, I've been working on this for forever, and I've tried to use the Cindy method, and it is not a quadratic function. It hardly ever fits anything quadratic. And you can look at it, you can see, if you look a little longer, you have this very, very straight arms to this thing, just showing you that this cannot actually be quadratic. So what you can do is you can compare the results that come out of the Cindy model and the conjugacy model. What I've done with the Cindy model is I've changed the variables in such a way that you can directly compare them just like by eyeballing it. Okay, so the actual model is quadratic. It just doesn't look exactly like that. I just changed it into this normal form. So you can compare. The only thing that's different is the leading variable or the leading value here. So both of these things, quadratic mappings that are returned, both of them are actually logistic mappings. That's the way that I've decided to present them. The only thing that's different is the leading coefficient. So now you got to ask yourself which one is better, right? Which one turns out to give you a more accurate model? Well, anybody who might be familiar with the logistic mapping has probably seen this picture before. This is our usual period doubling into chaos diagram. And it tells us that if you increase the leading coefficient of your quadratic mapping, you will undergo a sequence of period doubling bifurcations, eventually culminating in chaos as R goes to 4. Now, on the immediate eyeball test of your Cindy model, you're putting yourself somewhere right around here, which has, if you go up vertically, you can see that there's a disconnected component to your attractor, right? So if you can see it, there's a lower component and a upper component. So immediately that tells us that this probably isn't a great representation, because we can see that our attractor in this case is completely connected. Similarly, for the conjugacy model, we can see that we're much closer to the end of this diagram. The chaos has almost fully developed here, and you have one continuous connected attractor. Again, that shouldn't convince you that this might be a better model. But what you can do is you can say, pick some random initial conditions, you can flow them through the network, and you can ask yourself which one gives a more accurate forecasting. In this case, the yellow squares are the actual data gathered from just using a Runge-Kutta scheme to simulate forward and collecting data each time you cross the Poincare section. The white dots are the Cindy mapping. You can see that you basically fall off almost immediately because this mapping is extremely inaccurate, because the original Poincare section is not a quadratic polynomial. And finally, the teal, or whatever you'd like to call that color, is your conjugacy forecast, where you can see where you stay on for about 6 or 7 iterates. Now, of course, this is a chaotic mapping, so any little perturbation is going to lead to extremely sensitive results, and you're going to fall off eventually. You can find some initial conditions that stay on longer, but I wanted to show you one in the interest of honesty that stays off not quite as long. Okay, so this didn't have, or this just tells us how we can use this change of variable in order to warp this, this Poincare section data in order to better fit easy to understand models such as the logistic mapping. Then what you can do is you can turn to everyone else's favorite chaotic system, the Lorenz system. And much like the Rosler system, there has been decades of research into the Lorenz system. And we have a pretty good idea of what we should be expecting when it comes to Poincare section dynamics here. So here you can see the projection of the Lorenz attractor into the XZ plane. In this case, the Poincare section is given by the plane that connects the two fixed points in the inner lobes here. So I believe it's z is equal to 28. And you collect the x and y data. You have two-dimensional data. And if you go back and you open up your nonlinear oscillations, vector fields, and bifurcations or something like that by Guggenheimer and Holmes, there's an entire section in there talking about the Lorenz attractor and how the Poincare section dynamics should be topologically conjugate, should be, being the active words here, to a skew system of the form that's written on the board there. So we have a lot of properties about this system, and that gives us a pretty good qualitative understanding, but we still don't know what a system would look like that we are conjugate to here. So what you can do is you can feed this into the network, and you can find a discovered conjugacy with a relatively simple mapping here that follows exactly the same form. And so what I did is I used an expansion in the fewest variables possible. So in the case of the upper function G1, I went up to quadratic order, guaranteeing that I preserved that odd symmetry. And in the case of G2, I stayed at linear order. And essentially what the network is doing is it's not only finding those coefficients down front, but it's also warping the data in such a way that it is going to best fit the very limited library or expansion of functions that I'm giving it. And again, just putting this up on the board should not convince you that this was actually good. So what I decided to do is I decided to see if I could understand the topology of this attractor using this discovered mapping. And so what I did is I looked for the recurrent points in this mapping. And the lowest one is a period 2 point. It is a periodic orbit that whips around each lobe exactly once. Then what I did is I took the points in the discovered mapping, the conjugate mapping, I mapped them back to the proper Lorenz variables using the inverse of the conjugacy. And I used those to seed a shooting method that could initiate a root finding problem to find these periodic orbits. So what you're seeing here is the result of all of the periodic orbits found up to length 5, including the symmetry. So you can switch L's and R's to find another one with the same symmetry. You can find the period. You can see that it takes, using fsolve on MATLAB, your initial guess is so accurate, you're getting there within 7, 8, or even 9 iterates. Your fsolve time is 20 seconds at most to find these periodic orbits. So that's how accurate these are. You can go, I think I went all the way up to the period 11 points, but after that, my patience just sort of ran thin, and I just kind of lost interest in continuing to go up. Okay, so I can feel it. You're probably not that impressed. The Rosler system, the Lorenz system, they've been beaten to death. Maybe they're not that interesting to you anymore. But I sure hope that maybe partial differential equations might be something that is slightly more interesting to you. And in particular, if you like chaos and you like partial differential equations, Kuramoto Sivashinsky is probably somewhere that you find yourself very comfortable. And if you're not familiar with the Kuramoto Sivashinsky equation, I have it right here. The subscripts denote partial derivatives. And this is a 4th order in space, 1st order in time. It's a dynamical system. And typically, people assume that we are on a periodic domain. So we will make that same assumption here. And you have a single bifurcation parameter given by nu, which is referred to as your hyperviscosity parameter. Now, as I mentioned, you usually assume periodic domain in X. So one method that people have used to analyze this is Fourier-Galerkin projection onto finitely many Fourier modes. And the result here is a massive system in the Fourier coefficients that are time dependent. And some recent work from 2015 published in Chaos was able to show that as you decrease the parameter nu here, you undergo a sequence of period doubling bifurcations, eventually culminating in completely chaotic dynamics for this Galerkin projection. Now, one thing that should immediately jump out to you is the fact that you've seen this picture already before on my slides. You saw this picture when I was talking about the logistic system in relation to the Lorenz dynamic, in relation to the Rosler dynamics. And so immediately this got me thinking that maybe what's driving chaos, at least initially for the Kuramoto Sivashinsky equation, is exactly the same thing that's driving chaos for the Rosler equation. And in fact, you can confirm this, first of all, by calculating the Kaplan-York dimension. And in that case, you can confirm that the attractor is approximately one-dimensional embedded inside of this high-dimensional phase space. In my case, I used a 14-dimensional projection. You can check that if you go beyond 14, the dynamics look qualitatively identical. And in particular, for example, I have a specific value here. You can show that for this particular value of nu, you can actually establish a perfect conjugacy with that logistic mapping. And so essentially what this tells you is that the same type of chaos that's driving Rosler is at least initially driving Kuramoto Sivashinsky. And again, just like the Rosler system, you can use this to extract the periodic orbits out of this chaotic attractor. And what I found out recently from someone who did this independently at coincidentally the same parameter values that I was looking at is that their method of manifold projection predicted exactly the same number of periodic orbits that I was able to pull out up to period 6. So this is telling you how accurate this conjugacy is that you're able to establish between these things. And so what I'm showing you here is the chaos projected in the first and the 10th Fourier component here, and you have in blue just the lowest order unstable periodic orbit that's embedded in there. Okay, so the Kuramoto Sivashinsky equation is the place where I want to focus the rest of my talk. And in particular, this is really where I want to focus a lot of my research going forward. This is really the sort of playground for chaos in higher dimensional or in infinite dimensional systems. And if you ask certain researchers, they might tell you it's how we're going to understand certain aspects of chaos in turbulent or certain aspects of turbulence in fluid models as well. So this is the sort of stepping stone to moving up to much more complicated models and potentially helping us to understand turbulence in chaotic or spatiotemporal chaotic fluid models. So in this case, another extremely well-studied regime for the Kuramoto Sivashinsky equation is this other value of nu that's at the top of the board here. In this case, I'm plotting my chaotic attractor in the A1 and A2 space, so the first Fourier mode, the second Fourier mode. And you can see that there's a perfect symmetry between this space given by negating the value of A1. And on the right-hand side, you can see the space-time plot of this along this attractor. These blurrings that you see right here represent moving to one of these side components, whereas these sort of longer period oscillations in the middle correspond to being on more of these middle components. And so in fact, you can actually do just some simulations here. You can, first of all, the center component lies in the symmetric subspace. So it has this A1 to minus A1 symmetry in the image. And from simulations, we know that this thing is a chaotic saddle. So what that means is that everything eventually winds up on the sides here. The sides here are the real chaotic attractors, whereas in the middle, this acts as the chaotic transient. And in particular, from the symmetry as well, the left and right components, they map into each other via this symmetry. Now, as I mentioned, this is an extremely well-studied system at this parameter value because this marks the next sort of step up into more complex chaos. You are beyond the period doubling cascade that I showed you on the previous slide. And that means that we're sort of out of the realm of places where we have explicit and simple models to describe a lot of the chaos that we're seeing for these types of systems. Now, let me start by talking about the center component here. In a paper from about actually about 10 years ago, Lorenz and Tanovic, they were studying this system, and they used these really complex computational methods, projecting onto unstable manifolds and doing all of these decompositions. And they conjectured that the center component should be approximately a one-dimensional, it should have approximately one-dimensional Poincare section dynamics. And so what I sought out to do was to try and confirm these conjectures using these methods and find a conjugate one-dimensional mapping that can be used to understand the chaos in this case. So in this case, the Poincare section is given right here on the board. So it's when you have peaks of the A2 variable. And I'm just showing you the time series of A2 here. And in particular, what you can do is you can establish a conjugacy between this dynamical, so this Poincare section data and this discovered conjugate mapping here, which is a cubic polynomial. And in particular, what you can see is that you have a perfect y to minus y symmetry that is reflecting that A1 to minus A1 symmetry that you had for the full dimensional state space dynamics. And what you can do is you can use a lot of our sort of old school pen and paper methods from dynamical systems in order to understand the dynamics on the center component with this extremely simple mapping, right? This is a cubic polynomial. I've been working with polynomials since I was in high school. I'm very good at this now. And what we can do is we can break up the components of this into three areas broken up by the peaks and troughs of this cubic polynomial. And we can organize all of the periodic points using these symbols of 0, 1, and 2, depending on where each iterate lies. And of course, from the symmetry, you can exchange any sequence, exchange all the zeros for twos and the twos for zeros, and you get a symmetrically related periodic orbit. And in particular, what I'm able to do is quickly and efficiently confirm all of Lorenz and Tanovic's results. So in fact, using my relatively simple discovered mapping, I can extract the UPOs, the unstable periodic orbits, and I can use my Newton's method, my root finding problem, in order to find all of the periodic orbits that it took Lorenz and Tanovic, an entire paper to flesh out how they were able to do it. And in particular, right in the middle of this chaotic attractor, the network finds, without me telling it, that this y equal to 0 value is this organizing steady state from the Kuramoto Sivashinsky equation that, again, Lorenz and Tanovic were able to find using some very complex numerical methods, and they found this to be the organizing center. So this is just something that sort of pops out of this conjugacy that I've implemented here. And so just in case you want to see some of these pictures of these unstable periodic orbits and where they cross the Poincare mapping, the red dots correspond to where they cross, and the blue is the actual unstable periodic orbit. So the longer the sequence, the more numbers of intersections with that with that Poincare section. And of course, for example, the symmetry relation here would allow me to also look for an orbit with 1, 1, 0, which would correspond to flipping the A1 variable. Okay, so another piece of this is the side components. So that if you read through that Lorenz-Tanovic paper, one of the things you'll notice is that the side components give them much more of a headache. And in fact, they weren't really able to extract that much from the side components because their numerical methods were falling short. But what they do before falling short is conjecture that the Poincare section dynamics should be approximately a quadratic mapping. So in this case, you can set up a nice Poincare section that is sort of cleverly chosen, and you can feed this data into the neural network. You can discover a nice quadratic mapping in this case, with just this really nice form. In this case, the coefficients are chosen by the neural network. But the really nice part about this, again, that I want to emphasize to everyone, is that you get the network topology, or you get the Poincare section and the chaotic attractors topology for free out of this. So one thing that Lorentz Titanovic's analysis was not able to do, it was able to predict the topology of these side components. And what you find here is that there's a single isolated fixed point for this quadratic mapping, and the two intervals that lie to the left and right of this single isolated point are completely swapped into each other by each iteration of this mapping. And so one thing that Lorenz and Titanovic talk about in their paper is that they couldn't find any periodic orbits with odd periods. Well, now we have an explanation for why that is the case, right? Based on this topology that we're finding of this swapping these two intervals, you are never going to find an odd periodic orbit except for the fixed point that lies in the intersection of these two intervals. And you can go even further. And again, this was just sort of limited by my own attention span, I suppose, but just pulling out periodic orbits out of this thing in a very routine manner. So you can find period 1, 2, 4, all the way up to 22. You can easily find 24 if you really want to, but I had to stop somewhere. And just to show you what some of these look like, they're much less exciting looking than the previous examples were. I will note that this is in A3 and A4 coordinate space. It's just the same coordinates that Lorenz and Titanovic used. But the weirdest thing about all of this is that if you compute the Lyapunov exponents associated to these periodic orbits, all of them are unstable except for one, which is very, very odd, right? Remember I told you that the topology of a chaotic attractor is that it's densely filled with unstable periodic orbits. Well, it turns out that that period 4 orbit is actually stable. It is something that actually Lorenz and Titanovic found as well, but the basin of attraction for this thing is so ridiculously small that you are never going to observe an initial condition converging onto this. And so essentially you're just going to observe the chaos bouncing between these chaotic or these periodic orbits. And the asterisk here represents the fact that these were not found by Lorenz and Titanovic. Okay, so let me wrap up. Just to finish up, the paper that all of this came from, or most of this came from, we broadly apply these methods to the Rosler, the Lorenz, and the Kuramoto Sivashinsky that I showed you. But we also do this for a delay differential equation. That's the Mackey-Glass equation. Again, you can show that the chaos in the Mackey-Glass equation is governed by that same quadratic mapping that's governing the Rosler attractor, that's governing the Kuramoto Sivashinsky equation as well for relatively large hyperviscosity parameters. Now, as I mentioned, there is a lot more work to do for the Kuramoto Sivashinsky equation. One of the critiques that somebody inevitably is going to have here is that most of the mappings I've worked with are one-dimensional. And of course, that's because we know a lot about one-dimensional mapping. So I had to start somewhere. I had to start with where the mathematical knowledge actually lies. Now, what we know about the Kuramoto Sivashinsky equation is if you continually decrease that parameter nu, the dimension of the chaotic attractor increases without bound. And so if I continually decrease it, I am going to have to fit mappings of increasingly larger dimension. And in this case, I don't have explicit prescriptions. I don't have work like Lorenz and Titanovic that laid out what I should be looking for. And I don't have explicit normal forms like the logistic mapping that help me, again, know what I should be looking for. So it's a lot more of a blind search. But nonetheless, we were able to do it a little bit in the paper. In this case, for nu equal to 0.21, you have a two-dimensional chaotic attractor. and overlaid with the chaotic orbit in white, you've got what we've called the bat, which is one of the periodic orbits that lie inside of that attractor. Okay, so where is it? What do I want to do with this, right? Well, I am a dynamical systems analyst. I want to analyze dynamical systems, of course, right? I think I've emphasized that enough. But where do I really want to take this? As I mentioned, I want to take this up to fluids. So we're working with the Kuramoto Sivashinsky equation. We're trying to push forward to see how far this can be taken. And in particular, we would like to be able to get up to, for example, understanding the chaotic attractor embedded in, say, Rayleigh-Benard convection. And why? Well, with Rayleigh-Benard convection, you have important questions about maximizing heat transport. And there's a number of conjectures that ask you if the heat transport, which turns out to be just a infinite time average, is maximized over any of these unstable periodic orbits. So of course, if you can build a library of unstable periodic orbits that you've dug out of these things, then you've got a way of just checking systematically who is maximizing heat transport in this case. And I would like to finally finish by saying I have a pipe dream, potentially, especially targeted at the members of this audience, of somehow using these computational results to prove something analytically, potentially using a computer-assisted proof. So, you know, I have this dream in my head of somehow setting up a neural network and saying if the loss is small enough or something like this, you know, we can use these computer-assisted proofs to potentially prove that these conjugacies really do exist. Because of course, this is a critique that you're going to get from a more mathematically inclined audience when talking about these kinds of things. Okay, so thank you all for your attention. Of course, as I mentioned, Steve Brunton and Nathan Kutz are my co-authors, and they were my advisors during this. And then I had some undergraduates working with me for some of the latter part of the Kuramoto Sivashinsky equation, who should not go unmentioned. They did some really, really fantastic work here. Thank you.
Thank you, Jason. Are there any questions in the audience or on Zoom?
Sure.
Yeah.
So I'm curious about how the network is being trained, like on what data?
Yep. Oh, so you're curious about what the data is?
Yeah.
So you essentially just, because it's chaotic, you're going to transiently fill out the entire attractor if you just run it long enough. So you just sort of start with one random initial condition on the attractor. So you might want to let it evolve to the attractor, start there, and just let it run for a very long time and gathers. Of course, with all of these things, the more data, the better. So you want to let it run for a long time. But the nice thing is, you know, sometimes with the Cine method or something, you want to do a whole bunch of different initial conditions. But the nice thing with dealing with chaotic systems is you're eventually just going to sort of ergodically wander through phase space. You can just do one long trajectory most of the time.
And then I also wanted to ask, how generalizable is the network once it's trained? Like, is there a family of sort of dynamical systems that you need to restrict yourself to, or like how broad does it go?
Yeah, so it's certainly not generalizable. It's the conjugacy is specific to the data that's fed in, right? So you're conjugating the original X variables, or whatever you want to call them, into some latent variable. So it's not like I couldn't feed it ssler and then try and feed it Kuramoto, right? Because it's trained on the ssler variables. So it's very, very specific. Yeah, it's I tried to emphasize this, but it's qualitative over, or sorry, it's quantitative over. It's qualitative over quantitative. Sorry. Yeah.
Yeah. So one of the motivational examples was like this piecewise affine map that you said couldn't get with your polynomial ansatz, basically, right?
The 10. Yeah.
Yeah. I mean, there are like piecewise polynomial, mappings with which you could try to approximate.
Yeah.
I mean, devil's advocate, I guess, is that practically completely useless, or because we've had a talk a year ago where somebody would approximate everything with piecewise affine functions or piecewise polynomial functions. I mean, there's a lot of stuff there.
Yeah, I completely agree. Yeah, maybe I was being a little over dramatic when I was talking about that. But my point was, you know, a lot of people in the model discovery community, which is where Nathan and Steve are both coming from, these are a lot of engineering type people, and they're not really interested in doing, like, they want to keep it as simple as possible sometimes, right? And especially, you know, it's true, you can set up these piecewise polynomial mappings, but then it's just an enormous headache a lot of the time to set up this basis of expansion, you know. And then you have the same problem. What are you using for your basis? Where are you breaking up your piecewise components? You just have all of these headaches that crop up, and typically, you know, my experience with the community is that people just go, okay, I'll explain it to polynomials, and hopefully Taylor's theorem tells me if I include enough polynomials that I'll get a good approximation, right? Without thinking about the fact that Taylor's theorem is a local result or anything like this, right? But
What is the role of lambda when you just discard all the coefficients of the polynomial which are small enough? What did you choose, and
oh yeah,
the ones that
you're talking about for the Cindy method?
yes.
Yeah, so in this case, it's a hyperparameter. So what you need to do is you typically roll over lambda. So you step it up or step it down, and you look for whichever one.
Lambda is small.
Yeah, you minimize error over lambda.
And for the Rossley example, where you have this nice polynomial of degree 2, is there a way of finding these coefficients through an analytic method? Was it part of your question, because you use a training to get them?
Yeah, so they're entirely found through the completely sort of blind training process. So I would, if somebody has an answer to that, I'd love to know, so that I could double check some work, right? But honestly, I don't know.
It's an approximate conjugate map.
Yeah, everything is approximate, right? Everything is up to some training error, right? So I don't want to be too overzealous about how important some of this stuff is. It's all just computational.
Yeah, so we have,
Or sorry.
oh, sorry, no.
Go.
Okay, thank you. So we have two questions in the chat. So the first one is, are there issues coming from noise in data?
Yeah, so again, my motivation is particularly just understanding dynamical systems. So I haven't, I'm not like putting noise on it to test if it's robust or not. I suspect, you know, I suspect some robustness to small levels of noise, particularly from the fact that, you know, my process of just gathering the data is, I imagine somebody could do it much better than me. I'm just doing a very simple if less than or equal, and then next one if greater than, you know, so it's nothing too exciting. But honestly, it just hasn't been something that I'm too interested in, because I'm not using real data. It's synthetic data all the way through. This is something that I would love to get to in the future, though.
And the second question is, have you looked at systems with many positively Lyapunov exponents, like you can get in time delay systems?
Yeah. This is sort of what I talked about when I wrapped up. When you have many positive time Lyapunov exponents, then the Kaplan-York dimension is big, right? And that tells you that the latent mapping is going to be relatively high dimensional. And so this is again where I want to get to. I only have one experiment on Kuramoto Sivashinsky with this so far. But like I said, the drawback here is that, you know, we have 50 years of people studying interval mappings. And I know everything there is to know about interval, or we know as a mathematical community, everything there is to know about interval mappings. But other than maybe like a Heenan map or something like that, there's still a lot to be explored, even with two-dimensional mappings. And so this becomes the issue going forward, is to know what you're looking for. Because you could do a blind search. You could just say, expand yourself in polynomials, but then you run the risk of making your mapping complicated all over again.
Yeah, so going back to Kuramoto, where you computed periodic orbits, in practice, these orbits that you get, that you recovered, I mean, Magellan and Zitanovich got, right? The period 1, even further.
Oh, yeah.
Period 1, period 2, period.
These ones?
Yeah, so in practice, do you use the conjugacy and the map G for that, to recover them?
Yep.
Yeah. And
so, oh, sorry, I'll let you finish.
So basically, you kind of apply what you find them, what with Newton.
Yeah, so you take your
on the G level.
You find your intersection with the Poincare section. So you find your fixed point. Let's start with that. Okay, I find y star here. I undo it with the inverse conjugacy. That gives me a point in the Poincare section. I use a shooting method to flow it forward to the Poincare section again, gives me an initial guess, start the Newton iteration.
Okay.
And so if it's a period 2 point, same thing, bring them up, start the shooting method, et cetera, et cetera. So it's just a way of finding really good, accurate initial guesses for your Newton iteration.
So say if you were to apply that to Navier-Stokes, then that would kind of require, I mean, that would be very computationally, the shooting would be very, very slow, right? Would have to integrate.
Yeah, I completely agree. So if there's a better way to do this, I'm all ears. But yeah, essentially I was just trying to showcase how accurate these things are and how it's replicating what people already know.
I see. So, but to train it, so let's say now it's a 1D system, you're trying to move toward really Bernard. So in your experience at this point, how much will it explode the computational time to train your algorithm? Or it will be
I would like to train even the most complicated so far, it's under a minute. So
Okay.
I don't think it's,
okay.
I didn't mention this, but for the second set, for this set of the Kuramoto Sivashinsky, I think I'm using 16 modes, and I'm working on another region for the full, not for the odd subspace, for the full subspace with another friend. I think we're using 30 dimensions. Again, if I wait more than 2 minutes for the training, I lose interest, and then it's it's quite fast in terms of training. But yes.
Just one other question. I think I asked this question to JP also at some point. I mean, you at some point you want to like solve the root finding problem, and your method of choice is always Newton's method, right?
Well, mostly just because it's getting the job done.
Okay, but is it clear analytically that you're actually solving a root finding problem for a smooth function that satisfies all the conditions that you need? I mean, that's a snarky question, but I'm just interested.
I'm not sure I quite understand. Can you which root finding problem are you thinking about?
Well, which one are you thinking about?
I was thinking about finding the periodic orbits.
Okay, and that is a scalar problem, or?
No, that would be in the ODE system, right? So you're looking for a periodic orbit of your Rosler system, for example, or
Okay,
Lorentz.
at some point you have to discretize it,
Yep.
and it's a vector valued root finding problem. Then the question is, I mean, you throw Newton's method at it, but is that analytically clear that it's safe to do that? Are your roots non-degenerate? Are you continuously differentiable?
Or you want it because maybe the conjugacy is actually not smooth and it just kind of.
Well, I mean, of course, that would be my second question, but I'm just interested.
I mean, I think that the answer in this case would be, it's smooth because you cannot have this conjugacy, which is smooth, and then the flow itself is like, that's a smooth process, right? Because PD itself has smooth data in it. So the Cauchy problem is smooth, and then you go back with this map that is conjugating you with this quadratic. So this black box is in fact smooth, theoretically. But if, say, it did not have a PD to start with, and it was kind of training out of some data, which you don't know where it's coming from, then it could be the case that it's not smooth for someone.
And how do you know that Jacobian is invertible?
Okay, so well, that would come from the isolation of the periodic orbit. So if the orbit, if the orbit are objects which are kind of isolated in the phase space, then they're, then if they're hyperbolic, that's related to singular light exponents, then you have hyperbolicity and you have a local isolation. So Newton will recover that. But say if you have a hyperbolic PDE, or if you have a conserved quantities, then your periodic orbits may come in families. And in that case, these objects won't be isolated, and Newton may have struggled to actually converge. But in that case, that's a dissipative PD, and then the periodic orbits are isolated in the phase space.
Okay, so the system.
Yeah, so that machinery, but there could be cases where that's.
So this map H is a K diffeomorphism. We're not just asking for invertible, we're asking for smoothness. Yeah.
Well, so
For the inverse, that is also seen.
from the neural network itself, right? It's just an affine linear map, then composed with an infinitely differentiable function, right? And then you either make the affine dimension large and or just compose it over and over, so it's infinitely differentiable. at every step.
That was the question I was going to ask. I don't think you talked very much about the regularity of the conjugacy.
Yeah, sorry, I didn't think it would be that interesting, but I appreciate you asking. Yeah. So the regularity comes from the fact that you're just, this is the universal approximation theorem that basically underlines all of machine learning that says, if you increase the dimension large enough in this affine map, and then you have this composed with an infinitely differentiable non-polynomial mapping. So typically people use like arctans sometimes, or these exponential like 0 if x is less than 0, and
Sigmoid things.
yeah, all kinds of these things. So in my case, I always use SELU. There's a paper that says to always use SELU, so I say always use SELU. And but these are all infinitely differentiable functions. So you're just doing compositions over and over with infinitely differentiable functions. The conjugacies are themselves as well. At least on paper.
The approximations that you obtain are sort of.
Yes. Yeah.
Do we have time for one?
Otherwise it can go offline.
I mean,
I suppose we're honestly, I have nothing to do. I'm happy to talk. I'm happy to answer.
So actually my question is related to two other questions. One was on the approximate inverse property for H. And one was for the robustness to noise, because so in particular I'm interested to the velocities. So I think that's the trickiest thing to compute in practice if you really want to apply this kind of method to real data, kind of going beyond the time series, but actually getting the velocities to start the method. And that's where you will have to use some kind of approximation if they are not directly available. I guess in the synthetic example, they are. I mean, the velocities are.
Which velocities are you talking? So this is a discrete mapping, right? So there's no discretization of the.
Oh, so you don't need the velocity to set up?
Yeah.
Oh, okay.
Yeah, it's a discrete mapping, right? So you're going from the section back into itself.
Okay, because in Cindy you need the velocity.
Yeah, that's a huge drawback with Cindy. Yeah. So if you're going to do that with Cindy, Roman Grigoriev at Georgia Tech and a few other people wrote this really nice paper of what's called weak Cindy, and they turn it into an integral operation, and they solve the integral equation, the same thing you would do with a variation of constants type thing. They show that that's much more stable to both noise and approximating the derivative. Actually, you don't need to approximate the derivative. You do the.
Okay, that's interesting. Okay, because I was thinking, okay, now you've seen that you need the velocity as well.
Yeah, this is a nice thing about working with the maps, right? It's just literally applying the function. There's no derivatives that need to be computed.
Okay, so we should probably wrap it up now. If anybody has any other questions for Jason, he said, as he said, he's not doing anything right now, so come up to the front and talk. Thanks everybody for attending.
Thank you very much.